Most GenAI prototypes work until real users arrive. Then latency spikes, costs climb, and reliability becomes hard to predict. In this course, we'll unpack the architecture choices that move a fragile prototype into a controlled platform, 62% lower cost and twice the reliability. We'll move from symptoms to system design. First, we'll diagnose why GenAI apps fail in production: cost, latency, outages, and drift. Then we'll design efficient serving, add reliability patterns, and finish with observability, quality monitoring, and financial impact. By the end, you'll have a production-ready architecture proposal. The course is intentionally diagnostic. We start with what breaks in production, because architecture should respond to real failure modes, not just follow fashionable tools. When cost spikes, we examine routing, caching, batching, and model choice. When timeouts appear, we introduce queues, deadlines, and circuit breakers. When GPUs crash or run out of memory, we look at vLLM, isolation, and capacity planning. And when quality silently drifts, we need tracing, versioning, and monitoring. Each module turns one symptom into a clear engineering decision. Use this course strategically. If you are newer to production LLM systems, move sequentially and pay close attention to the diagnosis sections. They explain why each architecture decision exists. If you are intermediate, compare Module 1 to your current system. Then spend extra time on serving and reliability. If you are advanced, treat the course as a review checklist. Keep notes, redraw diagrams, and keep asking, what failure mode does this prevent? When you ask for help, include symptoms, metrics, and constraints. Most teams begin with the fastest path to a working demo. A user request hits the app builds a prompt, calls an external model, waits for the result, and returns an answer. The flow feels simple, and that is exactly why it is useful as a baseline. But every production concern is hidden inside that one request path: provider latency, ad hoc retries, prompts embedded in code, no cache, no routing, and limited cost control. From here, we can improve deliberately. The appeal is real. With this setup, there are no GPUs to manage, no serving stack to operate, fast prompt changes, and enough reliability at low volume. For demos, that can be perfect. In production, the same simplicity becomes the failure mode. Traffic spikes amplify latency and cost. Retries multiply load. Logs do not explain behavior. And model or prompt changes stay buried inside application code, where they are hardest to govern. The naive architecture treats the LLM like any other stateless API dependency. A request arrives, the backend builds a prompt, injects context, calls the commercial model, parses the answer, and pays for the tokens. What's missing is control. There is no place to reuse a similar answer, route to a cheaper model, shrink the prompt, enforce a budget, or skip inference altogether. Traffic and spend scale together, and unnecessary token cost becomes the default. LLM costs can also hide inside a single user action. A user asks one question, but the application may call the model several times, classify intent, rewrite the query, retrieve context, generate the answer, validate it, and repair the format. Each step adds tokens, latency, and another chance to fail. These chains often grow gradually as teams patch quality issues. But billing sees every internal inference, not just the user-facing request. This is why LLM cost is multiplicative, not linear. One request may trigger several model calls, and each call has its own tokens and model price. If requests double, prompts get longer, and the chain grows from 1 step to 5, the bill can jump far more than expected. Retries make it worse, especially during timeouts, parsing errors, or provider slowdowns. The practical lesson: track cost by request, feature, and chain step, or you may only understand the system after the invoice arrives. Another common production trap is tangled service code. A method starts as a simple model call, then quietly absorbs the model name, prompt text, retry behavior, parsing, validation, and error handling. Now, a small tuning change requires a code deploy and may affect multiple product paths. Worse, cost and reliability policies are invisible because they live inside handlers. The fix is to pull these concerns into centralized orchestration. where prompts, models, retries, and observability can be governed consistently. Business logic and inference logic answer different questions. Business logic decides what the product should do for the user. Inference logic decides how that request should be executed, which model to use, whether to check cache, what timeout to apply, what fallback to allow, and what cost limit to enforce. When those decisions live inside every feature, teams reinvent reliability and cost controls repeatedly. Separating the layers keeps product code focused on intent, while a gateway applies execution policy consistently across providers, models, caching, and monitoring. External inference APIs are valuable, especially early on. The risk appears when they become the entire serving path. Then the most expensive and latency-sensitive part of the product is controlled somewhere else. You may see response times and errors, but not the full machinery behind batching, routing, GPU utilization, model placement, or incident handling. With an owned inference layer, the team can tune scheduling, add fallbacks, manage versions, plan capacity, and optimize cost. The goal is not to avoid providers. It is to avoid being operationally blind and dependent. The big gap in many early LLM systems is not the model. It is the layer that decides how model calls should behave. If every feature talks directly to a provider, routing, retries, timeouts, caching, budgets, and fallbacks get re-implemented over and over, often differently. A control plane turns those choices into shared platform policy. The application asks for a capability, and the gateway decides the best execution path. That is how teams move from scattered API calls to an LLM platform they can optimize centrally. In production, prototype architecture fails in recognizable patterns. Costs climb faster than usage because retries and prompt chains multiply calls. Latency becomes unpredictable when a provider slows down, and retries can turn one outage into many. Debugging gets vague because LLM call failed is not enough to explain what happened. These symptoms tell us the architecture, not just the model, is now the bottleneck. You've completed the first diagnostic lens. Simple LLM integrations can work, while still hiding serious production risk. Direct calls tie traffic to spend. Chains multiply latency, cost, and failure points. Logic buried in code limits optimization. As a next step, audit where LLM calls happen, how many occur per user action, who controls retries and routing, and whether cost is attributable. Next, we quantify how token cost compounds.